Hello, teacher and everyone. I'm Tanvi, and today I will present for group 3 to present our papers. Okay, our paper is about the parameter settings for genetic algorithm layout planners as told in the 10 modes of manufacturing. Okay, include introduction. The second part is theory about genetic algorithm. The first one is application to our problems. The next one will be the result analysis, and of course, the last part will be our conclusion. Okay, now we will move to the first part, introductions. Our goals into manufacturing and logistics systems is to reach the long-term sustainability of the enterprise, and it requires continuous improvement of the enterprise processes and systems so that the enterprise can remain competitive in a dynamic and volatile market environment. However, we still have the problems in reality. Okay, here are our problems. The first problem is the rapid adaptability of business processes. The second one is the system for dynamic environment change. For detail is the changing of the customer requirement. Okay, and from these two problems, it will lead to the third problem that we can easily see that it will increase the labor intensity, time consumption, and cost. And the last problem we can see that are quality growth, complexity, and the functionality of output. And one potential option that we can use evolutionary algorithm to optimize the space for logistics in manufacturing system. And nowadays, with the development of IT tools, meta-heuristic method can give the better result. Typically, we can use the genetic algorithm layout planner, GALP for short. The solution is mainly focused on sorting individual cells without considering the relationship between the cells. Okay. Now we move to the second part, is the theory about the genetic algorithm. What is the genetic algorithm concept? It is a method to solve an optimization problem. Genetic algorithms are inspired by natural selection. For example, a population of mice over generations, they reproduce, mutate, and evolve. Good mice, the good individuals of the mice population will be kept by natural selection. The poor individuals will be eliminated by natural selection. In other words, good genes will be passed on from generation to generation. In the end, only the good individuals remain. It means that the good characteristics of the previous generation will be kept to the next generation. Okay, and as you can see, look at the slide. This is the flow of the flow concept of generators. At first, we will have the star. Inside will be grades population. The initial population is t equals 0. And after and in the population we have a lot of individuals, and after we have the individuals, we will have the fitness functions calculations. The fitness function calculations is you will calculate the fitness of each individuals, because each individuals here we have different fitness to the population. And the higher fitness and the higher solutions we have, the higher fitness we have, it means that the better solution we got. And after calculating the fitness of the individual in just one first population, we will come to check-in conditions to end. Sometimes the conditions means that the given number that we give to the systems. The T is Tmax. And the next step we will select. Is here we will choose the best one to do the best individuals to cross over and mutate. And it will continue as a loop until we reach our ending conditions that we give to the systems. Okay, that is the whole concept of genetic algorithm. In this figure, we will have, this is the crossover and mutation, but I will explain this more in more detail in the part when we apply this method to our problems. When we move to the GIS application to our problem, here is the flow chart of production layout design using a genetic algorithm. And the first we have our input will be the product material flows, capacity calculation, requirements for solutions, technological and building relationships among the worst teachers in the machine's dimensions. Here's our input data that we need to our float. Okay. And from the third figure, we move to the fourth figure is the generated algorithm for the layout optimization. This means that we develop from the previous layout to this, and from the fifth figure is our interconnections to the layout design procedure. As you can see that we have everything is automatic. People just need to update the data to the devices, and we calculate it based on the algorithm we developed for the machines. And afterward, we will have the result we need just in a short time. That is they have the technologies give us nowadays. Now we move to the step that we will set the parameters for the generated algorithms for our systems. First step is the generation of an initial population. Here we have interpretation of machines order and identifications. This means that we just assemble and machine 5 placing on the first and machine 4 placing on the last. They are just the random individuals that's in the initial population that we created first. Okay. So move to the second step, individuals evaluations of fitness functions. We have first equations in the evaluation to the intensity and the distance. We have this equations where n is the number of placed machines. This is the right angle distance between the workplace, and I will stand for intensities between the workplace, I, and shade. Equation 2 and 3 will be evaluated to the relations and distance. N is the number of placed machines. This is the right angle distance between the workplace, I, and shade. However, we have the V's. The V's notation is new field. V will stand for evaluation coefficient of a relation between the workplace, I, and shade. Okay, now we move to our final fitness functions value. Okay, we have to minimize our object function f, where alpha will equal to the ratio coefficients of part towards fitness function. Okay. And we also have the various restrictions in the layout constructions in the algorithm itself, as well as our constraints. So here we have that if the object is not multiply overlapping and place objects in defined by this minute dimensions of a production whole. We need to the verifications of the production holes here restricted. We also need the verifications of restrictions regarding transport strict arrangement in the production hole, and the last one is the verifications of restrictions regarding the definitions of the selected object fixed for positions in the production hole. We move to the third step is decision-making plots. We have 4 decision-making plots. The first, we will need to reach the maximum number of generation Gmax that we give to our systems. The higher permissible fitness value at B with the maximum value solution time Tmax. Assist the set iteration number Imax without improving a read solution. Now we move to the forces. Here now we look at the figure. We have 2 solutions that differentiate by the color. The green one is Scottish universal sampling, and the blue one is the Rocklet wheel selections. It's here we choose the blue terms of solutions that we can cross over and mutate in the following step. Now we move to the step crossover. Guys, here in the match crossing, we have, for example, we have 2 parent germs here. We will cross over them. We will have 2 children germs. And now I will explain in details how crossover work. Okay, we have 2 parent germs. P stands for parents and C stands for children. Now we need to the first block. Okay, we have the 5, but however we already have the 5 here, so we need to check them with the 5 of the second parent germs. We move to the first. We upsize the number. We have a 3. We have a 3 here. Okay, now we also have the number 2 here. We don't have any, so we can't replace it the 2 number here. And the next one we only have number 1, so it's really easy. Okay, 4 ones add their own rules. Now we continue one already have, so we need to check number one of the first transparent. Okay, the fifth and the fourth here, and the number two is nothing number two, so we can replace number two here. Here is how the course rules work in the genetic algorithm. Okay, and here is how it's applied to our problem where we give the machines work. We have the thickness here, and we also have the number of generations that we want. Table 1 is the various crossover probabilities in their result. In table 2, we also have the various crossover probabilities in their result. In here, we have experiment 1 and experiment 2, and I will tell you the detail of case 1, case 2 in the next step. Okay, the syntax we have a mutation here is the principle of the proposed algorithms. The mutation, this is mean we just select randomly the choice for the mutation. Is here we have the 2 and 4. And we just probability is 18 to 20%. We'll change their position and we will have value exchange or inversions. The seventh step is making a new generation. We have a table tree is the result of various mutation probabilities of the first case, and here are the second case. We also have the fitness calculations random here and the generation number here. We also have the average. Now we go to our finishes. Now we have the result of generated algorithm is here in the A picture. We have this is the block layout, and this B is the fitness value charts. Here we have the block layout after calculating by the machines. We have their persistent. Its color is 8 different blocks. Its design is in here. We can see the black line is the average, and the green and the blue one is our highest value. So its axis is for generation, and the fitness is for the y-axis. As we can see, our random average number like here is accepted for this case, and now is our result comparisons. Firstly, we'll compare with the PLAN or OPT algorithm, a method used in the factory FLAN OPT model, part of the factory design and optimization package from systematic metrics. And then we compare this shortened on the 3 criteria as distance, price, and times. After this comparison, we get the result and evaluate on the 2 test cases. The case 1 is a single manufacturing system. The system contains 3 product families, and each with the last 8% taps on 24 work planes. Why we have the case 2 here is the complex manufacturing system with 9 product lines and 60 work sites. This system represents a large production systems in practice. And as a result, it points out that GALP performed is better on every criteria on both test cases. Now we have our conclusions. From the result experiments, results show that proposed GAs provided a saving transfer performance in the case of less complex problem, which were 50 to 20% compared to classical heuristic result. It also leads to solutions with easier and directed material flow, requiring a minimum number of directions that do not represent significant deviation from optimal parameters of material flows. Conclusion that the main aim of this paper was to describe the use of the GA in manufacturing and layout optimization for continual and sustainable development of the company. And we can see a layout which is designed by the GA is not ideal only, but also for stable development, and it decreased the cost. And in addition, it's also for implementation of those solutions which are sustainable in the long times. For listening.